Okay, now just still not sure why people chuckle when I write this. This stands for brief summary, right? Okay, now look at line integrals. So we have some sort of a path, okay? A path x of ti plus y of tj. Now there's a path parameterized in terms of t that gives us a path in the xy plane. Now I discussed some length, how we might get a length density, and then I never really did say, but I gave some indication. But you have a length density here. This is a delta of xy, meaning if you're going to cut a material out of, well, okay, it's just the length density, okay? It's the mass per unit length along this curve, along any curve in the plane. So, yeah, that's it. Okay, we're just going to regard that as our mass per unit length. Okay, so how do we figure out the total mass in this figure? Well, we partition, obviously, the interval from A to B, which is the interval over which the path is defined, the interval of our parameter. We partition our parameter. And we're going to get, I'm not going to write out the partition and stuff, because in our context right now, we've seen a lot of that. So we know we're going to have a typical subinterval, with a sample point, a simple, a typical, I'll get it out here in a minute, typical ith subinterval with a sample point t sub I star and length delta t sub I, okay, interval of our parameter space. And that's going to give us an interval out here in two-dimensional space, a delta s sub I interval. And I write down that the delta s sub I vector is the x prime of t sub I, y prime of t sub I, j, all multiplied by delta t sub I. And I just kind of asserted that and then decided, well, I needed to give it a little more explanation, so we come over here and get it. So here is one end of the ith interval, here's the other end, or here's the position at one end of the ith interval of the parameter interval, and the other, okay? So this vector here would be the vector from the origin out to this point, which defines this point. That's x of ti minus 1 times I plus y of ti minus 1 times j. And from this point to this point, well, that's x of ti times I plus y of ti times j. And of course you have a delta y sub I and a delta x sub I corresponding to the vector delta s sub I from here to here. And it's easy to see what delta y sub I and delta x sub I would be in terms of these two expressions. The magnitude of delta s sub I is then, well, magnitude of delta s sub I is just how long this is. This is a right triangle, so this is the hypotenuse of a right triangle. It has delta x sub I for one leg and delta y sub I for the other, so its area is what I've written down here, delta x sub I squared plus delta y sub I squared, square root thereof. Now, the big key for setting up these integrals and getting expressions we can actually integrate is to be able to express our delta s sub I, and actually to express our delta x sub I and delta y sub I in terms of the x of t function, the y of t function, and its derivatives, their derivatives. Well, we know then that if ti star is a sample point, so if ti star is a sample value of our parameter in the ith t interval, if we evaluate x prime at t sub I star and multiply by delta t sub I, we're going to get a good approximation to our delta x sub I. That's all we're saying here. Okay? And that's just a differential approximation. And our delta y sub I is going to, again, be our y prime at whatever sample point we use, times our delta t sub I. So that our delta s sub I is approximately equal to x prime of t sub I star delta t sub I times I plus y prime of t sub I star delta t sub I, our approximation to the delta y sub I, multiplied by j. The magnitude of delta s sub I is then going to just be the sum, the square root of the sums of the squares of this I component and this j component. And I've written that down simply as x prime squared plus y prime squared because I was running out of room. But we understand that's x prime at t sub I star and y prime at t sub I star multiplied by the delta t sub I. And that's the expression that I wrote down here for my delta S sub I. Well, this expression, and this is the expression that I'm using for the magnitude of delta S sub I when I write this. Okay, right here it is. Now, to get the mass of the typical interval, we multiply the density by the length of the interval, which is why it's kind of important to find the magnitude of our delta S sub I, because that's the length of the ith subinterval. We multiply that by the density function evaluated at xy, where x is your x of t sub I star, you know, the x coordinate of wherever your sample point leads you on the curve, and it's going to be between here and here within this interval, and then the y of t sub I star. So we plug those in to the density function, we get the density, we multiply that by the length, and we got the delta m sub I, the ith contribution to the mass, okay? And then our total mass is the sum of all our masses, which is the sum of all this stuff in the usual manner. We see that what we're going to integrate is this expression, where the delta t sub I becomes a dt, and the t sub I stars become t's. And the expression that we get then looks very much like this. The only thing I've done here is instead of writing x prime, I wrote dx dt. Instead of y prime, I wrote dy dt. And it's implicit that these are evaluated at t. Okay, so now we have this representing our density, this representing our length. And we call the length ds, because of course it was a delta S sub I up here. So we call it ds. Okay, now what if we want to get the arc length of the ith subinterval? Well, we're just going to add up the length of, well, the arc length of the ith subinterval is just your magnitude of delta S sub I, which again is your xi prime squared, yi prime squared. Add them up, take the square root times delta t sub I. Okay, so when we set up the sum, our arc length is just going to be, well, the integral corresponding to that expression. And of course, we could write that as the integral of ds. But of course, to integrate it, we're going to want to use this, so that now, if we know our x of t and y of t functions, we can find their derivatives, square them, put that under a square root sign, and try to integrate it with respect to t. Now, sometimes you get something you can do the integral of, sometimes you're going to have to maybe approximate it. Because integrals, of course, are not guaranteed to be something you can evaluate in closed form. Okay, now, I gave this explanation. You've got a curve, you've got a tangent line. The tangent line at a given point is your x prime I plus y prime j, which we understand. Your tangent direction, okay? Normal direction is perpendicular to the tangent direction. A lot of times we want to find flux integrals, how much of something is flowing across the surface. So we're going to want to integrate the dot product of some function with m. Now I used v for a velocity function, thinking of a fluid flow. In general, you're going to want to do